Awesome. Well, next up, joining us is Dr. Jens Koch, who is an associate professor in the Department of Physics and Astronomy at Northwestern University. His research interests in theoretical condensed matter physics include strongly correlated quantum systems, quantum information processing with solid-state devices, as well as transport and coherence in nanoscale systems. Don't want to say too much, so without further ado, please take it away.
Will do. I assume you can hear me? All right, then I'll share my screen here. Let's hope that this works as well. So now you should be able to see my screen. Is that right?
Yeah.
Excellent. And so Diana, there's one part where I'll try to show a video, and if that doesn't work for some reason, you just have to cut me off and we'll do without, all right? So Diana and everybody, thank you for having me here. Thank you for the introduction. It's an honor and privilege to speak to all of you today and share some of my excitement about physics. You know, the simple truth is you are the future, right? Soon enough, you will shape this world with your ideas. And so I think getting you interested in science is incredibly important. And I'm very happy to try and do that. So my plan is to tell you the story of quantum computing, or at least a shortened version of it. In fact, there's much more here than one can fit into a single talk, but that's okay. So I'll give you at least a flavor of what quantum computing is. You know, with that, let's get started. So what is quantum computing? What is a qubit? What does superconductivity have to do with that? And hey, why do we care about any of that at all? So this would be the critical moment where Diana will try this video. There's somebody more famous than I am for sure who can tell us a little bit about what quantum computing is about. Let's see whether this works.
I can't hear the audio, but I can see the video.
Say again, Diana?
Oh, I said I can't hear the audio, but I can see the video.
Okay, so this is not working. That's too bad. All right, but I'm prepared for that. So this is actually a video of Justin Trudeau trying to explain what quantum computing is all about. It's sort of amusing if you've never seen it before, because the colleagues around him kind of smile and pretend to be proud that I guess he learned all of this by heart. I'm not sure how much he understands of it. And so some of the things that he says are here, and we'll actually go through them one by one. So one piece that he mentions is that our regular computers, our regular computer bits, in fact, are either 1 or 0, on or off. And that is certainly something that most of you have heard about before, right? A bit is the smallest unit of information. It's a binary variable, meaning that it can take on just 2 values, 0 or 1. And at the very core of our computers, everything boils down to zeros or 1. All the information is processed in that way. And Mr. Trudeau then continues to say that a quantum state can be much more complex than that. So let's take a look at that and see what that might mean. And for that, I'd like to introduce you to the concept of a qubit, which is short for quantum bit. And that's really just a quantum version of the bit as you know it. I'll represent a qubit by the circle with 2 horizontal lines that they're meant to represent energy levels. There's a lower one, there's an upper one. And then, you know, in quantum mechanics, we like to decorate our states with these funny brackets. So there's a state that is called 0, there's a state that is called 1. That's all very similar to a bit. And you might ask, well, this is very symbolic. What could a qubit be in real life? And in fact, there are lots of researchers who use different kinds of systems as qubits. So you could select electron energy levels in an atom to work as a qubit. You could use an electron spin. You can use photons as qubits. And what I'm particularly interested in my group is to use superconducting circuits as qubits. So 0 and 1, that looks very similar to the classical bit. What's special about a quantum bit, about a qubit? So in fact, this symbol here on the left-hand side is just our name for the state of the qubit. And you see on the right-hand side, there's something peculiar. This qubit does not have to be in state either 0 or 1. It can be in both states at the same time. Quantum mechanics allows for that. And in fact, these two quantities, alpha and beta, they're complex numbers, and they regulate how much 0 is part of that state and how much 1 is part of our qubit state. And since complex numbers, just like real numbers, are from a continuum, every qubit can actually take on an infinite number of states. So that certainly makes a quantum state more complex than that of a bit. And that is amplified when you think about more than one qubit. So let's start with one here, and let's add a couple, a whole bunch if you wish. I'll call the number of qubits, I'll give that the symbol capital N. And the state of this entire system of n qubits is complicated. So there are all these different states. The first one here is where all the qubits are in the ground state and the 0 state. This one here is the last qubit is in the 1 state. All the others are in the 0 state, and so on. And you know, there are as many different choices here as there are binary numbers between 1 and 2 to the n. And so there are, in fact, 2 to the n complex numbers that have to be specified to represent the state of an n qubit system. And last year, Google does research on qubits, and particularly superconducting qubits, and they presented a quantum processor with 53 qubits. And if you want to store that information and code it in these 53 qubits on a classical computer, you need a lot of memory. In fact, you need 140,000 terabytes worth of memory to store all these complex numbers. So that's pretty impressive. And so Mr. Trudeau then continued to say in the video that is missing here, but he says quantum mechanics allows us to encode more information into a much smaller computer. So that's what's exciting about quantum computing. Now, I wasn't born in the US, but have lived here for a while. I understand that in this country, size is very important, but I'd like to convince you that size is not everything. So what about this much smaller computer? If you think about your desktop computer or your laptop, then that is actually not much smaller than a quantum computer today, which might look like this. This is one of the quantum computers at IBM. In fact, the thing where the quantum computer is hiding is this cylindrical vessel that's a dilution refrigerator, which just makes these qubits very cold and behave more quantum mechanically. And so that size comparison is not so much in favor of the quantum computer. But in fact, maybe the better comparison is between this quantum computer and a supercomputer, which needs a huge room. And so that is certainly bigger than the quantum computer. Now, I wanted to argue that size is not everything. A very important aspect of computing is runtime, right? So here's once more the supercomputer on the left, and then on the right, you see Google CEO with, well, their version of the quantum computer. This is, again, a dilution refrigerator, which is now open. So you see all the wiring that goes down to the qubits. And the Google team invented a somewhat contrived computational task for this quantum computer to solve. And they did so. And they estimated that this huge supercomputer at Oak Ridge would need about 10,000 years to solve that computational problem. And the Google machine could solve that problem in 3 minutes and 20 seconds. So runtime is an important aspect of computing, and quantum computers can do certain tasks a lot faster than our current computers today. And so let me try to say a few words about, you know, what makes a quantum computer faster, what makes a quantum computer tick. And one aspect of this can be understood in the following way. So let me represent this quantum computer as a simple machine that takes some input here and then it'll spit out some output. So this could be a simple quantum algorithm of some kind. And so let's suppose that we feed in the state 0. And what the computer will spit out is, well, it will apply this algorithm U to our state 0, and out comes U applied to state 0. Simple enough. Now we can rinse and repeat and stick in state 1, and out comes the algorithm applied to state 1. So far, that looks very much like what you could do with a classical computer. Now the clue is here. Instead of sticking in 0 or 1, you can stick in this combination of 0 and 1, a state that has both of them at the same time. And out comes, well, one component where the algorithm has been applied to state 0, and another component where the algorithm has been applied to state 1. So this is what people call quantum parallelism, where the quantum computer, in a way, processes all possible inputs at once. Now that sounds fantastic. It turns out that life is a little bit more complicated. There's some legal footprint to this. One can show rigorously that this ingredient alone would not yet be sufficient to actually make anything faster. I'm not going to prove that. I'm just telling you this as a bit of information. So a second ingredient that is required for quantum speedup is a property of quantum mechanics which seems a little bit mysterious, but we've gotten used to it. So let's see what we can do with 2 qubits. The simplest kind of state for such a system of 2 qubits is what is called a product state. So qubit 1 is in its state, and qubit 2 is in some other state, represented by the 2 different colors here. An entangled state is different. In an entangled state, the 2 qubits share this overall state with each other. We can't really say qubit 1 is in one state, qubit 2 is in the other state. They share this overall state. And I like to compare that with the situation that we sometimes see with dog owners and dogs, which somehow become very similar. And if the owner does something, the dog does something. If the owner looks one way, then the dog looks the same way. So that's a little bit like what entanglement is about. Now, I told you that in my group, we are working together with experimentalists on developing circuits that will act as qubits. And if you think about a circuit, then maybe this is what you have in mind. Now, this circuit would be horrible for a quantum computer. And that has to do with something that you're all familiar with. So if you're sitting there with your laptop, you can maybe put your hand on your laptop, and what you'll notice is that it's warm, right? Why is it warm? Well, because there's Ohm's law, and Ohm's law says that electric energy in a resistor is converted to heat. All our metals are resistors, so our computers produce heat. And that is a very bad thing if you want a system to behave quantum mechanically. So some people say that quantum mechanics is fragile. Whenever stuff happens like emission of heat to the environment, then most of the quantum effects actually go away. And that is why it's so useful to build these circuits out of superconductors. So if you take a metal like aluminum or niobium, you cool that metal down, then it will become superconducting and it will lose all its ohmic resistance. So if you have a loop of aluminum in the superconducting state, you kick on a current, then that current will go around the loop forever. And if you build your circuits in this way, then they do behave quantum mechanically, and they're a little bit like artificial atoms. So they have discrete energy levels, just like a hydrogen atom does, and you can manipulate by shining certain types of light on it, in this case, microwaves. So you take a microwave generator and you send a microwave signal to the circuit, and that way you can perform algorithms and read out the state of your quantum processor when you're done. One thing that I'd like to mention briefly is that you can actually play with a quantum computer yourself. This is something fairly new still. So IBM has a quantum computer where you just go on this website displayed on the top right. You open a free account with them, and there are lots of tutorials if you feel like you don't understand quantum computing yet. So they have a lot of information there, and you can actually carry out your own quantum algorithm of your choice on a small quantum computer. They're not very big yet. They're not hugely useful yet because the number of qubits is limited. But we're making progress towards larger quantum computers. And so let me finish with a couple of slides telling you about what are quantum computers good for, right? That's an important question. That's why we're interested in them. So one example has to do with encryption and breaking encryption. So RSA encryption is one flavor of encryption which is safe currently because it's hard to decompose integer numbers into their prime factors. Now, for 15 equals 5 times 3, I managed to do that in my head, and that's no problem. For 21,809, I'll probably take a little bit longer. But then if you make this integer number larger and larger, it becomes exponentially hard to find the prime factors. And that is behind why RSA is secure. And it turns out that quantum computers can accomplish this task of prime factor decomposition very efficiently. That's known as the Shor algorithm. What else are quantum computers good for? They can perform certain types of database searches a lot faster than our regular computers today. So quantum mechanics is good at that as well. They can solve linear algebra problems faster and more efficiently. And you know, solving systems of linear equations is something that is needed all over in science, in many, many places. One modern example, one exciting example being machine learning algorithms, which do require linear algebra along the way. So if we had a quantum computer, we could also enhance machine learning and make that more efficient and faster. And then finally, another example is with a quantum computer. It's actually very easy to simulate quantum processes, something that is hard with our classical computers. And so you might be able to use a quantum computer to predict chemical reactions and to predict properties of chemical compounds, which really would revolutionize drug development and various other aspects. And so I see that I'm not quite running out of time, but I'm roughly on time. So I hope that this gave you a flavor of quantum computing. I think you now all know more than Justin Trudeau about quantum computing. And finally, I thought I'd end with a slide that shows some of the aspects of being a physicist and some of our activities. I'm really looking forward to questions from you. So it seemed like most of you like to post your questions in the chat. If Diana allows, then I'd also be very excited to actually get to meet you, so to speak, and have you ask your question in person.
Hi, okay. Sorry, my dad just walked in. Oh, someone just asked, what are the little brackets that you use to represent states for?
The little bracket, yeah. So there's of course a story behind everything. So this little bracket, its true name is a ket. I believe it was introduced by Dirac, the famous physicist and mathematician Dirac. And this ket comes with a partner, which is the bra, and together they are a bracket. And so it's just a fancy way of denoting a quantum state. All of quantum physics essentially is linear algebra. So you know, if you're familiar a little bit with vectors in say, two-dimensional or three-dimensional space, probably you denote your vector by putting a little arrow on top. In quantum physics, these states are actually vectors, but in a different type of vector space. And instead of putting arrows on top, we decorate them with this funny cat symbol. It's just notation, really.
Oh, someone asked, would you say that it is important to learn Python for this type of science?
It's certainly useful. I think learning some programming language is useful, not just in physics, but in various sciences and even for regular life. I have this little piece of Python code down there in the bottom right, because in my group, we've developed an open source Python library for superconducting qubits. We're very proud that this has been online for download for a while now. The last time I checked, we had about 15,000 downloads so far. And so, a lot of the work that we do as physicists can be done with pencil and paper. But as soon as problems become a little bit more difficult, right, then there's some programming, some numerics involved to solve the problem that way. And so that's an important skill, I would say. Yes.
Oh, someone asked, how does the US stand in quantum computing? Heard that China's way ahead of us.
All right. Well, there is competition for sure. But the US is very much aware of that competition. So you may have heard of the National Quantum Initiative, which has started to pour billions of dollars into the field to stay and be competitive. The most recent effect of that bill is, I believe in the next 2 weeks or so, the DOE, the Department of Energy, will announce which of the many proposals are going to be funded and create large national centers for quantum information science. So there's a lot of funding that is being invested into this field, which is very exciting. There's lots of opportunities for young people to join the field and become quantum scientists, quantum engineers. We're definitely looking for you guys to become interested and join us.
Awesome. Someone also said or asked, how much does it cost to build a quantum computer?
Oh, quite a bit of money. I don't know how to do this calculation really. What I can tell you maybe a little bit about is how much does it cost an assistant professor to get their lab started these days. So the dilution refrigerator that you need, assuming that you're interested in working with superconducting qubits, that dilution refrigerator costs somewhere in between $300,000 and $500,000. And then, there's about that much that also goes into microwave equipment. So you need fancy microwave generators and devices that shape the microwave pulses to allow you to talk to your qubits, to manipulate their quantum state and read that state out. So there's a price tag, and I think overall there's to build a large quantum computer that will cost quite a bit more money. But I think as far as quantum computing is concerned, we're sort of in the age of the very, very first classical computers, right? Where classical computers filled entire rooms. They consisted of vacuum tubes, and in the beginning, the CEO of IBM at that point claimed that worldwide we'll probably need 5 computers, and that's enough. And now look at us where we are with all of our computers surrounding us daily. And I think that's at least the way I view the status of the field. We're really just at the very beginning.
Awesome. Oh wait, there was one more question from the YouTube. How do you get involved with quantum mechanics early on?
How do you get involved? That's a good question. You know, I'd be happy to dig out some books and make recommendations. I think my question back would be, what do you already know? Do you know a little bit of linear algebra? That's a very good prerequisite to have. But there are other books that are more at a general level and tell you about history and general concepts of quantum mechanics. And I think that can be a nice starting point. Or if you're adventurous, right, then you can really just open an account on the IBM website for their quantum computer and start playing with it. It's a beautiful situation where, you know, when I started doing research in this field, there was no such thing. If I wanted to play with a quantum computer, I had to, you know, visit experimentalists and see whether they would be interested in carrying out a certain experiment that I thought could be cool. But these days, you have access to these processors. IBM has a very nice collection of introductory tutorials, how to understand qubits and manipulate them. And so I think that could be another exciting way to enter the field.
About whoever just asked about the link for the IBM website, I also put it in the YouTube chat, and I'll also just comment it in the comment section. Oh, and we have one last question, and then we have to move on to Dr. Holtz. But we had a question of, do you take any high schoolers
oh yeah,
to help you with your work?
Definitely.
Oh.
We've actually worked with 2 high school students from the local area here in the recent past. They have, under our guidance, they've played with the IBM machine, and they also helped us with our superconducting qubit library, so they knew a little bit of Python. So there are definitely opportunities.
Okay, awesome. Sorry, this question I've seen like multiple times, but because someone asked, what happens when we use minus sign in place of addition? For what?
Minus sign in place of addition. In the context of quantum mechanics? This sounds like a very general question.
Yeah. It gets bigger. Like, all right, there's no follow-up. So, all right. Thank you so much, Dr. Koch. I hope everyone really enjoyed learning about quantum computers.